So now let's look at what Strong Leibniz says. So Strong Leibniz has A equivalent to B as a hypothesis. So from any hypothesis involving an equivalence, Strong Leibniz tells us that we can use conditional substitution to substitute each of these well-formed formula into the same well-formed formula C, and we get an established equivalence here. So the key thing here is that A equivalent to B can now be a hypothesis, and the restriction here is that we need to use conditional substitution. So we have to be careful about the well-formed formula C that we're substituting into to ensure that, for example, if C involves a quantifier, that the variable in the quantifier doesn't get captured in A or B. So again, the proof of Strong Leibniz is by induction on the complexity of C. And we also call Strong Leibniz with conditional substitution. So again, let's look at an example where we need to prove the following theorem schema. So here we have a hypothesis. P or not P implies R or Q equivalent to bottom. And from this hypothesis, we want to prove this equivalence. So x equal to y and R or Q is equivalent to x equal to y and bottom. So again, just like in other Hilbert-style proofs, we're always going to want to start with our hypothesis. So we want to write P or not P implies R or Q equivalent to bottom as a hypothesis in our theorem. So we may notice now, so notice that here's what we're trying to prove. How could we use the hypothesis to help us to do this? So where is Strong Leibniz going to come in, for example? So notice that this hypothesis doesn't help us to establish an equivalence because it doesn't involve an equivalence itself, but in the hypothesis, this part involves an equivalence. And notice that this is what we want to use. Notice that in our theorem here, we're trying to establish that this side is equivalent to that side, and notice that x equal to y and are common, and what's different is R or Q and bottom. But notice in the conclusion of our implication of our hypothesis, we have exactly that R or Q is equivalent to bottom. So first we need to unpack this hypothesis to be able to write this equivalence in our proof, and then we can use Strong Leibniz to substitute it into the corresponding formula we need to conclude what it is we need to conclude. So here, how are we going to be able to conclude this? Well, we would need to use modus ponens, for example, but we also need the hypothesis. But notice, P or not P is an axiom. So first, we write P or not P as an axiom, AX1. It's an axiom in propositional logic, right? So we know that it's a, for example, tautology in predicate logic, so that falls under axiom AX1. And then, since we have the assumption and an implication by modus ponens, we can conclude the right side. So R or Q is equivalent to bottom. So this is through 1, 2, and modus ponens. Since this equivalence comes from our hypothesis, we now know that we can apply Strong Leibniz to prove this equivalence here. So notice we substitute R or Q equivalent to bottom into the equation x equal to y and p, for example. So we use 3, we need a hypothesis, the equivalence we need, and we need Strong Leibniz where our C part is x equal to y and p. Notice that here we didn't write p fresh because we know that p is fresh with respect to everything we use within the Strong Leibniz assumption. So A, B, and C, p is fresh. But it is good practice to write p fresh in each of your proofs, simply to get into the habit in case you do need it. Okay, so that concludes the difference between weak and strong Leibniz, and we'll look at a number of examples in class.